one actually had a lot of content. It's a shame I woke up at 3:30. But anyway, the topic for today was going to be the second part of AR. Some of the more fundamental technical parts of why it works and why these HMDs, why they can do what they do and how we deal with some of the problems that come with merging the real and virtual world. So, some of these topics include light field rendering, which is a cool approach that's actually quite old, that's used to deal with problems related to the divergence accommodation conflict. We'll talk about optics, which is it's a whole field that builds up the foundation of why you can how you manage the light that's being sent to the user's eyes and what they can see and things like that. How you handle distortion. So last time I briefly touched on how you can tell if there's distortion more easily in AR because you have a real world reference point for how things should be aligned or what a straight line looks like or how big an object is or whatever. So distortion in AR is really important to deal with. We have some calibration concerns, or how do we do calibration of really complicated lenses. We saw a couple of lens designs last time. Also, we use markers in AR a lot. It's worth knowing how they work. And how do we track these headsets? It's surprisingly similar to how we track headsets in VR. Especially nowadays with the Oculus Quest. So last time, just to briefly go over the content from last time, we talked about the XR spectrum, which is a sort of idea for the most part that you have some scale from the real world to the virtual worlds. The closer you are to the virtual world, well, it's easier to think of it as the real world and the virtual world are two separate independent components, which are both can be displayed simultaneously, and the AR part of the spectrum, or more appropriately, the MR part of the spectrum would describe how well the real world and virtual world are blended. So if there's no mixture, then you are either in only the real world or only the virtual world. Or I suppose you could think of it, or I guess, this is not worth going into, but I guess you could argue that pure AR is also no blending at all, because pure AR doesn't have an understanding of the real world, and it's just an idea of how these three different components come together, the real world, virtual world, and how they're mixed together. In any case, we talked about pure AR versus MR last time. The main difference is that in mixed reality, you have an actual understanding of the physical and virtual world, and you mix them together somehow. So for example, you know where some physical object is relative to the headset, and you use that information to mix the virtual world information. Like for example, let's say that you have a controller, and in AR or in MR, I guess, you shoot a ball or a bullet or something, and it breaks, or the bullet just stops when it hits your physical wall. That's an example of MR. Whereas maybe in pure AR, you wouldn't actually know where the wall is, so you don't know where to stop the bullet. Anyway, that's just a very small example. You can look through this content again if you're confused about this. In VR and MR, or I guess it's a bit of a blurry line between VR and MR nowadays, because we have inside-out tracking, where the VR headsets do actually need some understanding of the real world in order to track correctly, like the Oculus Quest, for example. So, there's debate about how MR these VR headsets are and things like that. I'm actually not going to worry about this, and I should have brought this slide up last time, just to say that for our purposes, we'll assume that AR is just any situation where the real world is visible at all. Whether or not it's tracked, that can just be, AR versus pure AR. I'm just going to use AR as this general purpose term describing any headset in which the user can see the real world. And it's just to deal with this ambiguity. This should say VR, but there's this ambiguity, and I don't want to deal with it. So for this class we measure VR specifically because it's more widespread, it's in consumer stage, it's a little bit easier to work with, it's cheaper, and the skills do transfer eventually to AR, so that's nice. So what you're learning is not useless even if you did want to learn AR. The very first, what we call a VR display, is technically an MR display, because Sutherland was displaying this cube, which was superimposed on the real world and tracked. And in AR and VR, we need to deal with this problem called divergence accommodation conflict, where we are trying to get the user to focus on some 3D virtual object, even though it's not really 3D. We just trick them into thinking it's 3D by displaying it on a certain, we display it a certain way on the screen such that the user thinks it's 3D. But ultimately, their eyes are still, their focal distance is still stopping at the actual screen, because, you know, the 3D object is just, you know, it really is just flat in terms of how the physical object that is displaying it works. So divergence accommodation conflict comes from this mismatch here, and the biggest implications are that, like I said, well, I didn't say it, but if you don't get them to, if you don't design the screen such that they are trying to look at a 3D virtual object, then what will happen is that the user will their eyes will just focus on the flat screen itself. And as you know, these are very close to the user's eyes, so they won't be able to focus on anything. Then we have the opposite problem related to defocusing, where the user can focus on the 3D virtual object, but they can't defocus the parts of the screen that wouldn't be focused on if this were a real object. And so this is a problem that it's an important consideration when thinking about the optics or design of these headsets, and you know, where the lens is, how the lens is designed, how the light gets transferred, and things like that. And in AR especially, this is a huge problem because you can see the physical world, so you know whether or not things should or shouldn't be in focus, and if they're not aligned correctly, or if there's any distortion. So in AR, this is more of a problem, but in VR, it's still a problem, and we'll see some examples of how it's addressed in VR. Just to breeze through these displays that we saw last time, you have two main categories of displays. You have video pass-through and optical pass-through. So in video pass-through, it's like Pokemon Go, for example, where you obviously don't see the Pokemon in the real world. You look at your phone screen, which is displaying the Pokemon and where it should be in your real world, but you're not looking at the real world directly when you're doing this. You're looking at the screen, which is replicating what the camera itself sees, and this would be perfectly fine if there were no distance between the screen and the camera, but obviously that's not the case. The phone camera, for example, is offset. There's also some thickness, and another problem is depth, which might not be intuitive yet, but we'll talk about depth later. So video pass-through is simple, but it doesn't work for for real 3D understanding of the environment. In optical pass-through, the user does look at the real world directly. So pretty much any of the headsets that we care about are optical pass-through. So you can either see the virtual image reflected off of a combiner, or the virtual image is presented to you by shooting the rays of light directly into their eyes. And again, you can go back to these slides if you want to see these figures. And most MR headsets that we care about fall into this category. And in this case, we have, I don't want to talk about MR again, but the image that you're seeing from the virtual world, world in quotes, it may or may not be 3D. Like, you could just be looking at an image, it could just be a UI element, or it could be a 3D object. It doesn't matter, it's still optical pass-through. So for example, Google Glass, which we saw last time, is not really mixed reality, it's optical pass-through, but it's effectively pure AR, where there is no understanding of the real environment, you're just showing them UI. But the HoloLens is mixed reality because you're putting 3D objects in the world. So, example of the HoloLens, she is seeing the real world, but she's also seeing these 3D objects which were placed in this, basically placed in the real world, even though they're virtual objects, and she is looking directly at the real world, and the image that she sees of these objects is being reflected off of the combiner in the HoloLens. So just a quick recap on that. We saw these spherical combiners, which are these giant headsets where this big piece of spherical glass is the combiner and the LCD is reflected onto it, and some distortion is applied to the LCD image before it's reflected onto the combiner so that when the user sees it, it's not distorted. And these are nice because they're cheap and they have high field of view, but the problem is that they're gigantic, obviously. Some examples, there was this cheap one that we saw on Amazon. The Meta 2 also is one of these, and as you can see, there's an LCD and it's reflecting the image onto the combiner. In this case, the combiner is some subsection of the glass part, not the entire glass part. You can see the parts that's darker in this image. And again, you can go back to these slides if you care. There's the Leap Northstar, which is this very cheap large combiner headset that you can build yourself, and whether or not it's fun to build is up for debate, but it's a cool project. Most of the MR headsets that are popular and that you've seen around a lot, like the HoloLens and Magic Leap, are near-eye displays, so the combiner is basically right next to the person's eyes. And the goal here is to make the headset very small so that, instead of making the combiner this gigantic piece of glass that's way in front of the person's eyes that causes the headset to be like wide in this way, if you design it such that the combiner is next to the person's eyes, you can compress or you can compact the display or the headset by quite a bit. You can do this in a few ways. You can do it with light fields, which we'll see in a second. You can use micro displays, which are very little sources of light, basically, and waveguides, which help guide the light towards your eyes or the combiner. And then you can do it with a small combiner, or like I just said, you could project the image directly into the eyes. It depends on the design of the headset, but this is another way of doing it. And yeah, you can shoot the light directly into their eyes. And yeah, I already talked about this. These are harder to make, obviously, because we can't just shoot out the image onto a piece of glass and figure out the distortion. We need to design these headsets such that the light actually gets to the combiner correctly. We saw examples of these headsets which shoot the light directly into your eyes. We saw the HoloLens, we saw the Magic Leap, and Google Glass and Apple Glass. So all of these The near-eye displays have a couple of challenges, such as the brightness versus opacity. You want it to be possible to make certain parts of the virtual world opaque if you need to, but usually this is done by, or commonly, maybe not commonly, but a naive approach to opacity would be to just make that pixel on the combiner really bright. But the problem then becomes, is it safe for the user to be looking at that? Or, are you causing migraines by having really bright lights? Do you have epileptic users, things like that? So you don't want it to be crazy bright, but you also want the pixels to be opaque if you need them to be. Otherwise, they'll basically always be holograms. There won't be any real sense of presence. Their field of view is tiny, so we saw how the HoloLens field of view is 30 degrees, a third of the Oculus Quest's. And even the higher end headsets like the Magic Leap 1 and HoloLens 2 have really small field of views. And here's another example. The PlayStation VR has a pretty high field of view at 100 degrees. Imagine that you're looking at a virtual scene and you only see this tiny part of it. That's what AR headsets tend to be like. They have very weak hardware because they're mobile usually. And like I mentioned before, this conflict is more important. We saw this example of the HoloLens' field of view. This person is looking at this astronaut, which is pretty close to them. And as you can see, they can only see this tiny subsection of the astronaut. Whereas in a VR headset with a high field of view, you would be able to see the entire astronaut. And yeah, this is presence breaking. It's a problem that is constantly trying to be solved in the AR field. So, moving on. Last time I actually made a minor mistake that I'll correct here. Varifocal displays are these displays which can actually deform themselves to deal with focus problems. So this one is a varifocal display, for example, because it has hardware that does actually move to try to accommodate your eye tracking or eye focus. And yeah, they usually only have one combiner, I think. Like David Dunn's display, I think, had a single combiner that could be distorted. So we had some membrane here that could be distorted so that when you're looking at different parts of the virtual or physical world, it will adjust accordingly. In this case, it was trying to defocus these alien creatures, which were at different depths. These usually require some kind of moving hardware, and as you probably know from file systems or any other class that deals with moving hardware, these tend to break easily. Last time I said that having multiple planes of focus is, I forgot my transition. Having multiple planes of focus is a varifocal display, but it's not. These are called multifocal displays. So in these circumstances, or with these types of displays, you have multiple combiners that reflect different parts of the image that are at different depths. So for example, something that's very close to your eye will be on probably the closest combiner. Something that's really far will be on a farther combiner. And the user will naturally focus on the right combiner because they're trying to see that part of the image. And that part of the image is only being rendered on one combiner, so they just naturally switch between the planes of focus. And these usually require a lot of hardware, as we'll see in a second with this example. And at the moment, they're just not feasible at all to put into ergonomic headsets. The Magic Leap, I think, has 2 planes of focus, but their lenses are already pretty big. And there is this cool paper you can check out with a multifocal display that had like 40 planes. It was insane. They had to render like, I think they mentioned that their biggest limitation is that they need to render images at 1600 frames per second, which is a little ridiculous. Anyway, this is a paper from Oculus, which is pretty cool. And as you can see, they're rendering on each focal plane only part of the image or only the image that you would see if you were focusing on the image at that perspective or something like that. You can check out this video if you're interested, but I'll speed it up. So they're just showing an example. You can check this out, but what I found more interesting is the hardware setup. This is what their hardware looked like. So they had, I think this was for the left eye, they have some near combiner, then some other combiners here, like I believe this, I'm not great with optics, but I think that an image is being rendered from this light source and going through this lens and being reflected off of a combiner somewhere here or something like that. And so they have a couple of planes of focus, and the hardware is just like insane. And as you can imagine, you can't fit this into a headset. But it's still a cool, it's still a cool design and a cool hardware project. And apparently it worked pretty well. It's a paper from Oculus Research. You can check out if you're interested. So the other way of dealing with this in a more automated way is light field rendering, which is proposed in '96. The idea of light field rendering is that you sample an image. Well, you can render an image from the camera perspective, but as you probably are familiar with, or as you probably understand now that you've used a VR headset, your camera view is basically just your head view, or it's just your head orientation, but it doesn't tell you where the user is looking. And so light field rendering kind of deals with this by rendering the image from the camera viewpoint, the camera being the head orientation. But in order to deal with the eye, what they do is they basically apply a filter to each subsection of the image, such that when the user looks at one part of the image, the things that are not in focus will be distorted. You can check out this old video. So here they're rendering speed this up. They're rendering the camera viewpoint, so like your head viewpoint basically. And they're getting some information about the image, and you can check out this video. It's actually a pretty good video, but what they're doing is once they render the image from this perspective, they apply some filter to each subsection. And so if you want to focus on, say, this part of the image up here, your eye will look up here, and the filter that they applied to these other subsections are supposed to help you naturally defocus the other part of the image. I'm not great at explaining how this works, but you're welcome to check out the video, which explains how they do interpolation and stuff like that. But I think their original goal was to model how the light will actually bounce into the eye. So let me actually pull up this lecture. If you recall how HRTFs work in audio, light field rendering does something that's really similar, where they try to estimate what the light rays will look like for each of your eye orientations. So down here in audio. Oh man. There we go, HRTFs. So with HRTFs, it's almost like you render the audio, or you figure out how the audio sounds from each orientation around your head. And light field rendering kind of does the same thing. What it does is it estimates what the image will look like for different eye rotations. And so basically, once your eye actually rotates towards that part of the image that's relevant, it will just look right. But you're free to check out the example, or Levoy's video, which is pretty good. This guy gave a pretty good explanation of how this works as well. So he's showing how, let's see, this was an older implementation of light field rendering where they just render the image from basically each possible eye orientation and generate them that way. More recent methods try to generate these. What am I trying to do? Or I forget what I was trying to show in this image. More recent implementations will do it through the rendering system. I don't remember what I was trying to show. Maybe just those cameras. In any case, let's move on. You can check out this video though. He has a pretty good explanation of why it works. There was this other good talk for if, for your independent research. I don't remember if there was anything in particular that I was trying to show in this video. I think it was just a good explanation of why it works, or the math behind light field rendering. Yeah, more of them. You can check these out if you actually care about light field rendering. In 2013, they did come up with an implementation of light field rendering that is specifically for near-eye displays. So they finally, moved on from having that huge camera apparatus, and they subsectioned the display that is in front of the user's eyes so that it naturally helps with defocusing the part of the image that you're not looking at. So for example, if you focus on this part of the image, the other parts will automatically defocus. And yeah, you're free to check out these videos if you care more. It's hard to explain with videos that don't have audio. And also the videos are kind of long and the explanation for light field rendering is a little hard. But it is a cool method, and a lot of people nowadays are looking into using these for better AR displays. But anyway, moving on, there are these other AR displays called volumetric displays, which are basically the real-world implementation of holograms. And the way that a lot of these work is by basically shooting light rays from some light boxes or some source of light and designing the display such that it reflects those light beams or scatters them to eventually create what are the equivalent of 3D pixels. You can check out the papers that these came from if you're interested in how they actually implement them. There's another version of this display that I'll cite later, and I'll show you. It was kind of cool, but I don't think they had a video that explains well how it works. But they used a mirror that rotated really, really quickly so that users from any viewpoint can actually see them. These are also called autostereoscopic displays, which autostereoscopic basically means that you can get, basically anybody from any viewpoint should be able to get a full 3D view of the thing that they're looking at without any headset. So they don't require stereoscopic displays, which are rendering two different perspectives, one for each eye. The pixels are already basically 3D, so you already see it in 3D. The limitation of these displays is that they have pretty low resolution because you can only shoot so many light rays and it's hard to get them to intersect and things like that. But they're still pretty cool. So as you can imagine, the display internals are pretty complicated, and I won't go into any low-level explanation of how they work because it doesn't really matter to us as the high-end developers, or I should say higher level, not high-end. They have a bunch of tiny hardware that explains how the light gets bounced around and generates the image. And the waveguides themselves and their design, like this waveguides, are kind of complicated. And here are some resources that you can check out if you actually are interested in how they work in terms of the optics. And I have more resources coming. So, onto the optics part. Why aren't lenses flat is a question that I hear a lot. And I've asked this question before too because I didn't do great in physics. But the reason that lenses aren't flat is because of light physics. If you've probably seen this image before, in AR and VR, you can think of it almost like the focal point here. Imagine that your eye is here, and these are the light rays that are being bounced off of objects in your environment. The lens needs to be designed this way so that it guides the light rays into your eye so that you actually see an image. And the shape of the lens affects how those light rays converge onto your eye. And I have a resource here that explains why aspheric lenses are common, but this image here I think is good enough to explain. A purely spherical lens will just, it doesn't really cause the light rays to converge on a single point. It gets them to converge in a range. And what this causes is, it causes some distortion. And the word aberration is used a lot because aberration, I think, refers to less distracting distortions, like, for example, slightly doubled images, or maybe like defocused light rays, or things like that. I think aberration is just a very general purpose term for simpler distortions. But in general, a distortion or aberration, the semantics aren't important. These are just, they're caused by the shape of the lens being not flat, and what happens is that the image that gets rendered from this perspective is not actually what the person saw or what the camera saw, even though you don't really see what a camera sees through any way except the image. But everybody I think has experience with this, where you see something that looks really nice in real life and then you take a picture with your phone and then it looks like trash. That's basically what distortion is. Although usually the reason for it looking like trash when you take a mobile picture is different, but even so, the idea is similar. As for distortion, we usually think of distortion as being like the lines are not straight, like in this image, or the scale of something is messed up, or something like that. There was this meme about how like the moon looks really big to us in real life when we look up in the sky, and then when you take a picture, it's like this tiny little dot in the camera image. And distortion it's a really important topic in general, in pretty much any graphics field, including computer vision and optics. So it affects how we design the AR and VR lenses. Even in just pure graphics, when you're rendering an image, you need to think about the camera distortion. Unfortunately, game engines sort of just handle this for us, so that's nice. In AR and VR, especially in AR because we're trying to guide light rays, the Fornell effect is really important to think about. And Fornell it's this effect that you see here, or specifically here, where the light that's being reflected from a very extreme angle will have much stronger distortions. So for example, let's say the light source is this little white ball here, this little white sphere. If the light source were to move such that this were reflected on the front here, it wouldn't be nearly as distorted. It would look like a perfect circle. But as it moves to the edge, it gets super distorted. The explanations are complicated. There are a bunch of equations that describe why Fornell is the way it is, and what effect you hope to see from a Fornell effect. But the too long didn't read is that it's just a lot of physics. But all you need to know is that it distorts light a lot, and that means that we need to worry about this when we deal with AR and VR. Since in AR and VR, your eyes and the screen or the combiner, which are basically your light sources, are really, really close to each other, which means that the distortion, your lens is very small, and so that means that a huge part of the lens is probably going to be distorted when your eye is so close to it. And in VR, a lot of people wonder why the lenses in VR look like this. It is because of this Fornell effect specifically. These are called Fornell lenses, which are used for magnification a lot of the times, but for VR we use them for dealing with this distortion. What they do is, actually I guess you can check out some of these websites that I cited, but what these lenses do is basically they make the lens jagged so that the light doesn't bounce at such extreme angles. In AR, it's a lot harder to deal with these problems, and yeah, I don't want to go into a detailed explanation of why the lenses are like this specifically. It's pretty easy to look up yourself, but you'll find that the explanations are any explanation that's not perfectly high level will be very low level, like in the physics and the equations and things like that. By the way, this is an example of the Vive's Fornell lenses, and these are the Oculus Quests. The Oculus, I don't remember what they called them. I don't know if it was like pseudo Fornell or something like that. But they are still Fornell lenses. I think it's just that the jagged edges are a lot smoother or smaller or maybe denser or something like that. I don't really remember. Anyway, in AR, distortion is a little bit harder to deal with, especially Fornell distortion, because we need to design the lenses such that we undistort the virtual environment specifically without distorting the real world view. We don't want people, a lot of people have, if you wear glasses, you've probably had people ask to try on your glasses and them realizing like how screwed your vision is. That is distorting their real world view, right? Like when somebody else wears your glasses. In AR, we sort of have the same problem where we don't want our lens to have the effect of distorting the viewer's real world view. But we do want to distort the virtual environment because we need to, the light is being reflected, or I mean, the light source, you're not seeing a real image, you're seeing a virtual image, and in AR, the screen is not directly in front of your eye, or at least the light source of the image is not directly in front of your eye the way that in VR the LCD is directly in front of your eye. So it's just a harder problem to deal with in general. Some ways that this is handled at a very high level are you can design the waveguide itself. The waveguide is what guides the light rays from the light source to the eye or the combiner. You can design the waveguide and the light sources or the light emitters themselves to guide the light onto the lens with the assumption that the lens doesn't have much distortion. Like for example, your glasses or reading glasses or anything like that don't have much distortion. They're pretty flat usually. Usually the worse your vision is, the less flat your lenses are. But let's assume that an undistorted lens would just be like a flat piece of glass basically. So in this case, you're basically trying to handle the distortion all from the optics side. The problem here is that the hardware starts becoming complicated. Like designing the waveguide correctly can be hard, and it starts becoming harder and harder to make it fit compactly because you need some space to bounce the light rays into the right place. You know, this is an ongoing problem. How do you bounce light rays into exactly where the user's eye would be, with the understanding that the user's eye may not be perfectly placed, or people have different eye shapes and different face shapes and things like that. Another option is you can distort the lens itself in such a way that it doesn't actually hurt the real world view, and you can make them reflective, like in this example, and you know, you're still shooting the light rays onto a reflective surface, but you can figure out how much distortion this lens has by using some computer vision techniques. More commonly, we just mix both of these ideas. For example, the Hololens and Magic Leap just mix both of the ideas. I mean, they have some lens distortion, and they also have really complicated waveguides. It's probably one of the reasons why they're so expensive. So just to kind of illustrate the point, this is the Hololens, and this is its lens. The HoloLens and Magic Leap are both weird pieces of technology. It's hard to explain succinctly how they work, but the HoloLens does have a combiner which deals with part of the image. It also has a lens here. For now, we'll just talk about this lens that's here, not the outer shield, because that's a lot more complicated and it's hard to find a good explanation online of how it works. But let's just worry about this lens here. With the HoloLens, for example, there is some light that's being generated from up here, and the waveguides are designed such that they bounce around and create an image that's rectangular. So this is a good illustration of how it works. You have the picture generation unit, as they call it, or I would just call it a light source, and it's being shot onto the lens, or onto, I guess, the first waveguide, and the waveguide is maybe subdivided into different types of distortion until it eventually makes its way onto a real image that the user can see. There is this cool example of, I think these guys made like some 3D printable waveguide that you can just kind of put onto any headset. And this is a cool example of how he's just holding the light source, and the light source bounces around the waveguide until it reaches the lens. And apparently it's undistorted. There was a good video example of how it worked. But anyway, you can check out these materials if you're interested. I'm just going through a very high-level material. So how do you handle the distortion itself? Because remember that we try to use both ideas. And if we use both ideas, then we have to deal with distortion one way or another. So how do we actually handle this lens distortion problem? Typically, we do this with markers. Fiducial markers are basically any markers that, or they're basically images or objects for which we know the exact real-world shape and size and their features when they're undistorted. So for example, this checkerboard, we know what a checkerboard looks like when it's not distorted by the lens. This is very similar in concept to that graphics topic that we talked about way earlier in the class, where you can define a texture map for base textures or albedos or diffuse maps, which are basically the texture of the object before it has been applied to the object and before it has any effect of shadows or lighting. So that's why it's called base texture. Fiducial markers are kind of the same idea. It's just an image that is undistorted. And the basic process is you find inside of the image that you got from a certain perspective, you figure out where the marker is, and then you figure out the equation or the matrix that you need to undistort it in that image, and then you apply that equation to any other images that are generated for that lens. And as you can imagine, that means that you only need to do this once for each lens. Most most standard cameras only require a matrix. Those of you in computer vision will already know how to do this probably, but most cameras only need a single matrix to describe the distortion, because the lenses themselves are pretty uniform, simple shapes. In particular, they're usually convex shapes, like some sphere or a sphere. In AR, a lot of the lenses are so complex that they require multiple equations, maybe a single complicated equation or maybe piecewise equations that deal with the fact that they're not uniform. And you can find more details in computer vision classes, and there are a lot of online resources, many of which I cited around here if you're interested in AR. There are a lot of APIs that do this easily, which is nice. So you usually don't have to do this by hand. The most common way of doing this, or doing the calibration, is with checkerboards, because checkerboards are nice and simple and easily describable, and you know they're square and you can tell where the lines are and so on. So they're just nice. We'll talk about markers in the next slide, but the most common technique is you hold a checkerboard in front of the camera. Well, you hold a checkerboard for which you know the exact sizes of each of these squares, and you hold that in front of the camera. And if you're doing a lens distortion calculation, what you do is hold the checkerboard outside, like you basically put the lens itself between the camera, in this case the camera would be like your eye, and the lens. So the camera will be out here, for example, and your eye will be over here. And a lot of the times we approximate an eye with a camera. So say that the camera generates an image that sees the checkerboard, which is on this side of the lens. You're just finding an equation that figures out how do you undistort the checkerboard. Oh, whoops. Anyway, yeah, so you hold the checkerboard outside the lens and you calculate the parameters that you need to undistort it. This is called intrinsic calibration, where you're trying to figure out the distortion of the lens itself. And for lenses that are very complicated, or it's just good practice in general, to try doing this with a lot of checkerboard poses at different angles and different positions in the camera perspective, so that you can get the best estimate of the distortion. This is more important for non-uniform lenses, but even for just regular spherical lenses, it's helpful because you get a more accurate estimate. In a situation where you have a lot of cameras and you need to figure out where the cameras are relative to each other, so we'll see depth sensors soon, but we've also seen systems like OptiTrack, where OptiTrack is trying to track the user and their skeleton from a bunch of different perspectives. In this case, where you want to know where the cameras are relative to each other, this is called extrinsic calibration, and you do this by basically putting the checkerboard in such a position that at least two cameras can see it at any given point. And you basically keep moving the checkerboard between each pair of cameras so that you can slowly converge on some solution. So checkerboard right now, let's say that you angle this checkerboard upwards so that these two cameras have a really clear view, and then you rotate it around so that these two have a clear view, and then that these two have a clear view, and so on. In this very simple example from this website, the cameras are oriented in such a way that they can all see the checkerboard all the time. So it's easier in this circumstance, but a lot of the times it's not. And also, if you have occlusion, like for example, if this is OptiTrack and a person will be standing in the middle, occluding some of the cameras, I guess it wouldn't matter. Never mind. I was going to say that it would make it better to know. I was going to say that if there's occlusion, it makes it easier to know where where each pair of cameras is relative to each other, but that can be solved with simple math. So never mind. Anyway, for really simple extrinsic calibration where all the cameras are the same, it's not too hard to do this. When the cameras are not the same, like if you have different types of lenses for each of these cameras, maybe one of them is a phone camera, maybe one of them is like a real expensive camera, like one that you would normally take pictures with that are high quality. Maybe the other one is just a Hololens camera, which is really low resolution. that makes it much harder. In this case, what you would have to do is do the intrinsic calibration for each type of camera and then the extrinsic calibration. In situations where all the cameras are the same, you can almost do both parts at once because you know that all the cameras are the same. So, you know, it's kind of it's maybe like 2 matrix multiplications that can be done sequentially. So you can do it pretty quickly. Some common markers. I'm really close to the end, so I'm gonna try to rush through this. Some common markers are the checkerboard. The checkerboard is nice because lines are trivial, so it's very easy to tell it's very easy to get from a curved edge in a distorted image to a line on a checkerboard because it's not very hard to find the lines. There's high contrast so that the edge finding in computer vision is very easy. You know where the edge is because there's going to be a sudden jump from black to white. The problem with checkerboards is that they can be hard to orient. Like for example, with this checkerboard, you can rotate this. As we know in game engines or any of these other 3D softwares, these things do actually have orientation. So this checkerboard can be oriented in 4 different ways and still look the same. If you rotate this 90 degrees or 180 or 270, it'll look the same as the original pose. So that means that checkerboards can be a little bit hard to orient in, especially something like a system that has occlusion, where, you know, even if you have a checkerboard where you add 1 more row to try to handle the orientation problem, if the camera can't see that row, then the orientation is still ambiguous. So to deal with this, Aruka markers are common for orientation. These are kind of like these really simple QR codes, and they have a lot of the benefits of checkerboards, except you also know the orientation because they have this unique pattern that looks different from each rotation. And you can also change the density, so you can add more rows of pattern if you want to. I think you can go from 4x4 up to 7x7 is standard. More recently, there are these Charuko markers that were proposed, which are just checkerboard plus Aruka markers. These are becoming more and more popular. They're nice because you can use the checkerboard itself to get a really good initial estimation of the intrinsic calibration of the camera, and then you can use the Aruka marker to figure out orientation of this marker in 3D space, which is nice. The problem obviously is that if you know, these are pretty big markers, like this one takes up the entire image, you can't really make it too small because then the features won't be visible. What is becoming very common are image targets. These are probably some of the more standard markers that you'll see in practical AR development, like in game engines. Image targets are just images that have a lot of features, like this bundle of leaves. And they have these features, so just the edges basically. And what you do is in the camera image, you try to find the feature correspondences. And yeah, that's all there is to it. This is almost like a purely computer vision approach that doesn't have a whole lot of geometry associated with it. It's nice for really cluttered images, or when you already know the intrinsic calibration, or you know, if you just want to reduce assumptions in general, like reduce assumptions of how easily visible the checkerboard is. Like in this case, you're assuming that there's no other checkerboard in the scene at all. Although I guess you make that assumption a lot anyway. But anyway, image targets are just a nice general purpose strategy. And there's this really nice resource from Vuforia on how you make good image targets. You can use 3D objects for markers, and these are good for handling basically any pose of the marker itself. The problem is that it can be a little bit harder to define the features, and this is a topic that'll make more sense once we get into reconstruction next time. But yeah, let's say, like, I don't know if there's any kind of shading applied to this, or if the object itself is any more complicated than just a convex shape, it becomes harder to describe the features. And in 3D objects, it can also be hard to distinguish one edge from another. Like in this example here, this edge here is a little bit harder to make out than this one here, because the shading or the lighting is a little bit more similar between these two edges. Whereas in this case, this part is dark and this part's light. So that can be a problem sometimes. Finally, there are defocus markers, which is something that I've been working with recently. The problem especially with applications that require really small markers, like surgical training, for example, most cameras can't actually focus on markers that are more than like, or smaller than like 2 centimeters wide, or if they're too close to the camera. And so in situations where you try to use a regular camera to track a really small marker or a marker that's really close to the camera, the marker will become defocused in the camera image. And defocused markers sort of address this by just defocusing the marker itself so that at different focal range or different focal lengths it's not as distorted, or the edges, they make algorithms so that the edges don't need to be so well defined. In my case, for my own research, I've been using really close field of view cameras or focal range cameras, which work nicely with small markers. But another important benefit of these is a lot of cameras, like on phones, have autofocus. And so if you're trying to deal with problems related to autofocus, where, like, let's say that the camera, your phone camera is focusing on like your monitor, and you want to put this marker up to the camera, but the camera is still focusing on something that's farther, the marker will still be defocused. So that's what these markers are good for. Anyway, do I want to go through the rest of this? I'll just go through these marker tracking APIs and then we'll be done for today. So some common marker tracking APIs. OpenCV is nice. It's open source and it's compatible with basically everything. It has a lot of example code. The problem is that it's not very performant, and my understanding is that it's not great with multi-threading, but I don't know enough. I haven't used it that deeply or intensely to know exactly if that's true. But I think in general, it's assumed that OpenCV-based systems can be really hardware intensive if you're not careful with the implementation of what you're trying to do. Vuforia is also really common. It's probably the most common to be used with the HoloLens and Magic Leap. Unfortunately, it's proprietary, so you actually don't know how most of it works. It does work really nicely with really weak devices like the HoloLens. It's really good with occlusion, so if your marker has something in front of it partially. In my experience, I actually find that it can handle like up to 60% occlusion, which is really good. It's unfortunately really hard to use for just general purpose computer vision applications, partially because it's proprietary, and more importantly, Vuforia has this annoying limitation where you can't actually feed it camera images. You feed it a camera reference, like to the actual device, and it does all of the camera image processing directly, which means that it's a little bit hard to do any kind of filtering. Also, it only works with Unity, and it has a C library, but it doesn't work with Unreal, which is sad. In my experience, it's still the easiest to get working by far, and it has really good performance. It also doesn't require any manual camera calibration. My voice is breaking. So you don't have to do that checkerboard thing, which is nice. It's a huge plus. It saves a lot of time, and it also means you can work with dynamic camera poses. There's this other very common library called April tags, which is used in robotics. It's similar to OpenCV, but I think they specifically make it work with smaller markers, and it's supposed to have like 2 times better performance, which is pretty good. There's this API that I've seen around a lot called Maxed, which is kind of like Vuforia. I believe it's also proprietary. I find that it's way harder to use than Vuforia, and it doesn't seem to perform nearly as well, especially with occlusion. But it has SLAM, which is it's an environmental pose tracker basically, and we'll see it next time. But this also doesn't work with Unreal. Wikitude is this AR tracking or marker tracking library that was meant specifically for mobile devices and AR experiences based on location. So for example, if you want to show ads by, I don't know, the user pulls their phone up to some little image in front of your restaurant and it shows a little AR 3D thing. Or tourism, like a lot of if you go to a big city and you visit a museum or something, a lot of them have QR codes or like image targets that you point your phone to. And again, it pops up like 3D information about the thing that you're looking at. So Wikitube is meant for these things. AR Toolkit is basically the same as OpenCV, except they made it specifically to work with AR devices. The implication of that is that it has better real-time performance. For video pass-through systems, like on mobile phones, you have ARKit and ARCore, and these are really good at handling AR on their own systems. Like ARKit's really good on iOS, ARCore is really good on Android. They're not really good for anything else. OpenCV is pretty much the de facto desktop standard, but they are pretty easy to use, and they seem to be replacing AR Toolkit completely, and they're not as antiquated. A lot of these marker tracking libraries assume that the marker will take a decent percentage of the image space. So I find this is a problem with my own work, which is why I use small focal range cameras. But a lot of them assume that the marker will take like at least 10 to 25% of the image. And the implications of this are that the camera field of view, the focal range, and all the parameters are actually really important. And it means that very small or large markers are hard. So anyway, the rest of this I'll save for next time. So yeah, bye. Sorry I overslept.